we have a cylindrical pipe with the diameter of 20 centimeter, length of 1 meter, placed in a stagnant air or still air at 20 degrees C. The pipe surface temperature is 33.7, and what we have been asked is calculate the rate of heat loss from the pipe if it's placed horizontally or vertically. Now, it doesn't say anything about what type of convection happens, but since we know this is a still air or stagnant air, we know that's going to be natural convection if there is a convection that's happening in the system. So let's start by listing the known parameters. So what we know here about these parameters, what are given, Ts is 33.7 degrees C, T infinity is 20 degrees C, diameter is 0.2 meter, length is 1 meter. What else do we have? We have stagnant air. And what does that mean? We have natural convection. Immediately we can go for the natural convection. Assumptions. Assume we know the temperature surface is constant. There is a negligible radiation, steady state condition, constant properties along the surface of the pipe, and treat air as an ideal gas to get the expansion for beta. And we need to find Q. Q for two cases, like let's say for horizontal and Q for the vertical. Let's just not put VNH, confusing. Q is unknown here. Now, the first thing is finding properties. So TF, the film, is going to be Ts plus T infinity divided by 2. 33.7 plus 20 divided by 2 is going to be 26.88 degrees C, or 300 degree Kelvin. So we can read air properties. If you do, kinematic viscosity is going to be 15.89 times 10 to the power minus 6 meters squared per second. Prandtl number would be 0.07. Alpha is going to be 22.6 times 10 to the power minus 6 per second. Conductivity is 0.263 watts per meter Kelvin. And the other properties that we need is beta, the expansion coefficient, which for ideal gas is going to be 1 over T, 1 over 300, 1 over Kelvin. So this is going to be the properties for part A, that we have a horizontal. So this is the pipe that's putting horizontally with the lengths and everything. The first things that we do, we evaluate Grashof number. So Grashof number D is going to be G beta. Here I'm going to write T infinity minus Ts since the other one is greater than that. D3 divided by nu square. So would be 9.81. Beta is 1 over 300. 33.7 minus 20. D is 0.2 to the power of 3 divided by 15.89, 6 squared. So we would get 1.4194186 times 10 to the power 7. Then let's evaluate the Rayleigh number to see which equation we're going to use. Prandtl is that those numbers, so I'm just not going to rewrite that number that comes here times 0.707. We're getting 1.0035289 10 to the power 7, which is less than 10 to the power 12. So we can use, there is a correlation given for a horizontal cylinder, which is 0.6 plus 387 Rayleigh d to the power of 16, and 1 plus 0.559 Prandtl everything 9/16. This guy is 8/27 and power of 2. Now replacing this Rayleigh number here, and parental is 0.707. And if you do the calculations, the Nusselt number for this case is going to be 28.27. So H for this system is going to be Nusselt number D times K over D, 28.27 times 0.0263, and the diameter is 0.2. So it's going to be 3.7174 watt per meter square Kelvin. So this is going to be H, and Q is going to be HA delta T. So 3.7174. Area is going to be pi 0.2 times 1 meter. Delta T is 13.7. So we're going to get 26 watt in terms of the rate of heat transfer from this horizon if the pipe is placed horizontally. Now for part B, if we put the pipe in the vertical direction, now let's see what would be the heat transfer when it's vertical, and this is, let's say, L. Then let's evaluate Grashof number of L based on that. Characteristic minus GB infinity minus TS L3 divided by mu square. This is equal to Grashof number D, the one that we have evaluated before. So here everything else is the same, only D is replaced by L. So I can write down, and I know L is 1. Oh, sorry, L is not 1 actually. L is 0.8 in my calculation. So I'm just gonna make a quick fix here, 0.8. So L is 0.8. And I believe these numbers is based on 0.82. 0.8. So here L is gonna be 0.8 and D is 0.2. So if you do the math here, what you're gonna get is 9.08 427946 times 10 to power 8. I'm evaluating this Grashof number L because I want to see whether I can treat this cylinder as a flat plate. And there was a criteria for that. If we evaluate the value stratified over Grashof number L to the power of 1/4, here is going to be 0.2, which is smaller than 0.2 over 0.8. That's the ratio of D over L. What it means here, in fact, let me just write it in a different color. D over L, this is that ratio. Let's not be very confusing. This is L and this is D. And we know when this ratio holds, then we can use vertical flat plate correlation. So I'm going to use that. Then I need Rayleigh number, which is Grashof number times parental, and it's going to be 6.422585 58558 times 10 to power of 8, which is less than 10 to power 9, slightly less than that. So I'm going to use the Nusselt number for laminar from Churchill and Chu correlation, which is 0.68 plus 0.670 Rayleigh number L 1/4 divided by 1 plus 492 parental to the power of 9/16 and 4/9. So if I replace the Rayleigh number that I have got here and parental number, we know the numbers, then the Nusselt number is going to be 82.5, and H is going to be Nusselt number K over L, which is going to be 82.5 times 0.0263 divided by 0.8, 2.71 Kelvin. So from here, Q is HA delta T, 71 times I times 0.2, 0.8, 13.7. So what we are going to get is 18.68 watt. So this is compared with the other Q that we got at the top, 26 if we put it horizontally, and 18.68 if we just put it vertically. That's going to be the rate of heat transfer.